So Carlos in his talk had all these beautiful pictures of tapas to sort of, I don't know, whet your appetite for stuff. So my tapas is right here. It's a partially eaten chocolate chip chewy bar. So that might not be so encouraging, but I have something better. So Carlos simply gave you sort of ephemeral, non-physical things. I have prizes here for audience participation. I have given talks right after large lunches in hot climates before. It is not a nice place to be. So these are double espresso, doppio espresso, portatevi per favore. So you can come down, take one up, and drive away. Only caveat, Frank, prizes are available to graduate students. All right, so here's the game plan. First thing I got, because this is an old school talk, I wanted to save some time. And so there are a huge number of folks who have contributed to the implicitization problem. I'm not going to read them all off. They're all here on the board. And many of the, as David said in one of his talks, there's many people in the audience. So besides David and Alicia and Ron and Carlos, there's lots of people who know more about implicitization than I do. We also have an expert on Rees algebras, Quenon Lin, who is going to pretend like she's not an expert, but she's over there who knows more about Rees algebras. So there's lots of folks who know more than me, but I know just enough to be dangerous. So here's what I want to do. So here's the game plan. We have 6 parts. These are each supposed to be, I have 7 parts. This is for Macaulay too. I got to start my indexing at 0, right? So I have 7 parts. They're each supposed to be about 10 minutes. And what I want to start out with is the mission and a magic trick. So the mission is the following. So I have a polynomial ring R equals k of x1 up through xn. Inside there I have an ideal f1 up through fk. These are actually going to be homogeneous of degree d. So I have homogeneous polynomials of degree d. I have k of them. Of course, this then defines a map from k of y1 up through yk, which will be s, to r by sending yi to fi. So I have my nice map here. So I have a ring map. And the mission is to find, let's call this map phi, and our mission is to compute the kernel of phi, right? So it's a rather simple problem in some sense. We want to immediately recast this geometrically. So let's recast this geometrically. So instead, this map of rings is, of course, going to give me a map at the level of projective spaces. So I'm going from Pn minus 1 to Pk minus 1. It's a rational map, and the point is that these FIs could simultaneously vanish, right? So they can simultaneously vanish. The simultaneous vanishing of this is called the base locus. So the base locus B is V of I. This map is not defined there. All right, so I have this rational map. And the typical thing, the way that we often work with this, is to find the image. What we really have is we have a map from Pn minus 1 to Pn minus 1 cross Pk minus 1. By doing something silly, I take a point here, and I send this point to itself and phi of p. I'm abusing notation. I'm using this, and I'm writing the map here using the same phi. Right? So, and the image of this map, image over here of, let's call it, I'll abuse notation, is image of phi. Inside here is called the graph of phi. And then I have 2 projections. This is terrible because I didn't leave myself space, so I'm going to be, this will keep you guys awake, right? So I'm writing my 2 projections going upstairs. So I have pi 2, pi 1, so I can project onto Pn minus 1 and Pk minus 1. And what I want to do, of course, is find the graph, and then I want to project down onto Pk minus 1. That gives me my solutions, right? So that's the general setup, all right? So now what I want to do is there's all these objects that we saw in David's talk, and for some of them, we're kind of a very, we're doing bihomogeneous polynomials. We're kind of a bihomogeneous audience, right? There's people that are coming from very, very applied side. There's people who are pure algebraists of some flavor. And so what I want to do is discuss all these topics. So in each of these, if you zone out on me, it's shocking, but I found from having 3 kids that people don't always listen. Each of these you can jump back in. So these are each self-contained little biscotti to go with your espressos, right? So where's the magic trick? All right, so let me do a magic trick. This is even better. Percy Diaconis would not call this a magic trick, but it's better than a Percy magic trick because it's a theorem, right? So it's a magic trick that's a theorem. So let's do a concrete example of this. So I want to map P2 to P3 super concretely. And what am I going to use? I'm going to use, say, x, y, z, x, y. I guess I could write this like this, x, y, l, x, z, x, y, l, x, z, l, and y, z, l. Where L is just going to be the linear form x plus y plus z. I'm being terrible with notation already because I was using x's over here. For this it was x's, but now my x1 through x3 are really x, y, z.
So Hal, at least one of Percy's tricks is a theorem. The order of perfect shuffle.
Frank, I'm gonna not only not let you have an espresso, I'm gonna make you pay for more espressos. All right, so here's what I've got. Okay, so I have this map, and I want to know the image of this map. So I'm gonna do something right off the bat that we saw with David, but I want to make this notion of a free resolution a little more explicit. So this is an ideal in a polynomial ring in 3 variables. So I have a map from R to R mod I. R is just k of x, y, z. X, y, z for the Canadians, but z's dead, right? So now I want to do linear. All I'm going to do here, this free resolution business David mentioned, it's just linear algebra with polynomials. So I want to think of this as this is a 4×1 matrix of polynomials. So I have a map here, which looks like R4. I have my matrix. I'm just going to write this I in brackets for this matrix. And I want to do a little bit of bookkeeping here. So these are homogeneous of degree 3. I want to keep track of the degrees, and so it's counterintuitive, but the notation that these guys are generated, or gals are generated in degree 3 is right here. So this is just indicating these are cubics. And now my linear algebra with polynomials, and for the first espresso prize, tell me something that's in the kernel of this 3×1 matrix. No faculty. I'm going to even give you a hint. It turns out that there's 3 independent things, and what is this? This indicated a shift that they were cubics. The fact that this is -4 means that I only need 1 more degree to find them. So these are going to be linear relations. So I have linear in the variables relations, not linear in the sense of, you know, what we teach our linear algebra kids, but linear in the variables. Help me out. If you're bothered by this, what should you do when you're dealing with a complicated problem you've seen for the first time? You make it as simple as possible. So screw the 4 polynomials. Let's forget about these 2 and just focus on these. Right? Help me out. Somebody who wants a coffee. I know there's people that want an espresso. These are dopios, by the way. Help me out. I'll drink those coffees all myself, and it's going to get ugly. I said linear polynomial. Zeros in the kernel is not the answer I want. Help me out. Forget about these guys. X, Y, Z, and X, Y, L. What would be the sort of, and David mentioned this thing called, he said Kazul thing. So Kazul relations or Kazul syzygies are called, and something in the kernel is called a syzygy. So we got a good Scrabble word. The simplest, well, these are not going to be Kazul relations. They're almost Kazul relations. Help me out. Just look at those 2 guys. What could I do? I see someone with a, I heard somebody. L times the first minus Z times the second. Come on down and get your espresso prize. Yeah. You should always get the first prize because you know the questions are going to get harder, right? So good job. L times the first minus Z times the second. Everybody sees that, right? And then I just keep on trucking along, and you can see, well, right here, if I multiply, what am I missing over here? Z times this minus Y times this. So Z times that minus Y times that, and a 0. And then over here on the last one, I've got Y times this and a X times this with a minus sign, right? And it turns out, this is not a priori obvious, but it turns out that those are all of the relations. They span the set of relations. And there's no more, I mean, this matrix could itself have a kernel, right? This could keep on going, but it doesn't, so it stops here. So there's a famous theorem that David mentioned. Probably he should be on the board too. This is called the Hilbert-Syzygy theorem, which says if you're a polynomial ring in n variables, this process, not just for a quotient, but for any module, stops in at most n steps, with a caveat that we start counting to position 0. This is position 0, 1, 2. It stopped in 2 steps. It would have had to stop in at most 2 more steps. I'm in, or 1 more step. I'm in 3 variables here. So the Hilbert-Syzygy theorem says this process terminates. All right, so you're saying, where's the magic trick? So I haven't gotten to my magic trick yet. So now I'm going to do something that seems a little odd. Notice my variables, this is going to be, this is if you wanted, this is proj of k of x, y1 up through y4, right? Polynomial ring in 4 variables. So each of these things corresponds to one of these variables over here. I've got 4 polynomials. I've got 4 variables. So I'm going to write 1, 2, 3, 4 down the side, like that. Right? I have 4 positions here for these 4 syzygies. Everybody's with me on this, right? And now I'm going to do something kind of funky. I'm going to write these things, these relations, right? This is position 1, 2, 3, 4. I'm going to write these 3 columns as polynomials. So the first one I'm going to write as y1 times L plus y2 times a minus c, minus y2 times z. Right? This corresponds to the first column here. I'm just sort of using these things as placeholders for the positions. And then for the second column, I get y2z minus y3y. You guys should yell at me if I make a mistake. I know I'm writing, you guys in back should be yelling at me because I know I'm writing too small. y3, y, and then for the last column, I get y3, y minus y4, x, right? So what? You're already zoning out on me. And now I do something that seems totally out of left field. I'm going to reverse this process. So I'm going to take these things and I'm going to write them, I'm going to put them back in a matrix, but I'm going to collect, instead of the y1 through y4, the other set of variables, x, y, and z. Right? So what do I got here? For this thing, remember L was just x plus y plus z. So in each position for x, y, z, I'm going to have a y1. But I also have this piece. On z, it's a minus y2. So I got a minus y2 there. Right? So that's my first column. I keep on going now. So for this one, I've got a y2 in the z position. And I have a minus y3 in the y position. And for the last one, I have a y3 in the y position and a minus y4 in the x position. And I have 0. So I have engaged now in some random futile exercise after a big hot lunch for you guys. And just for the hell of it, since we've been taking determinants, I want to take the determinant of this bad boy, or girl, or whatever the hell it is. So the determinant of this thing turns out to be minus y1, y2, y3, minus y1, y2, y4, minus y1, y3, y4, plus y1, y plus y2, y3, y4. And let's call this polynomial h. All right, h is because it is the hero or heroine. So why do we like this polynomial? So here's the challenge for the board, or the disgruntled, or the bored and disgruntled. Plug in f1, f2, f3, and f4 to this guy. Lo and behold, it's 0. So that's a magic trick. That's my magic trick. So the question is, that's the implicit equation, right? That's the implicit equation. So what in the world is going on with this process of starting out with the syzygies, doing this weird flipping of the variables over to here, and taking a determinant? And that's what I want to flush out. I won't prove every piece, but I will discuss sort of the broad outlines of the proof to get to here. And I'm going to make simplifying assumptions all over the place. But the point is, this is sort of what I want to do today. Is everybody with me on this so far? Okay, so we're way behind time already. We're only done with our mission magic trick. All right, so let's do a turbo review because David already introduced them. So everybody is already an expert on Rees algebras and symmetric algebras, right? So I have to say, one of the things that I like about this is that I shouldn't say I was a Rees algebra denier, but I never was particularly inspired by Rees algebras. But there's some really cool hard problems in Rees algebras, and they tie into real-world problems. So I think there's a beautiful confluence in this area of hard problems in pure math, honest-to-God real-world problems in applied math, and that means for the young folks in here, that when you're thinking about things to work on, if you can do a good pure math problem, say it has an application so you feel like you're relevant to the real world and maybe get some grant funding, it makes you much more employable. So things to think about. Okay? It's true. It should have an application. All right. So quick review of Rees algebras and symmetric algebras. So what do I have here? I still have, fortuitously, my rings on the board. So the recent algebra and symmetric algebras are the following. So what I'm going to do is I'm going to take S tensor R. Right? This is just a polynomial ring in both sets of variables. I got my xn's and my yk's. Everything is in this setup over here. And what I'm going to do is I'm going to map this to R of t. David already did this. And the point is, what I want to do is R is sort of my base ring. And then so I got to tell you where the variables y go, and just yi goes to fi t, right? So this is a map that we saw on the board earlier that David had. And so let's call this map beta, and let's compute the kernel beta. And I'm just going to do it piece by piece. So I want to first look at the kernel beta 1. We've done this already. So what's the kernel beta 1? So I take something, and when I say 1, I mean degree 1 in the t variable. So I take somebody, summation ai yi. This gets mapped to, of course, summation ai fi of t. And the t is in every piece here, so it pulls out to the front. So the only time this thing is going to 0 is if this is 0. That means exactly that this is a syzygy on the fi's. So kernel beta 1 is exactly the syzygies on I. What about kernel beta 2? So summation aij yi yj is now going to map to summation aij fi fj t squared, right? Exactly, just pushing through. And so again, the t squared pops out, and we get a syzygy. But who's this a syzygy on? Somebody help me out. Not an espresso prize yet. It's a syzygy on? On the square of the ideal, right? This is in the square of the ideal. Square, syzygies by square. And we keep on going. And so the definition R of I is exactly S tensor R modulo the kernel of beta. And the symmetric algebra is S tensor R modulo the kernel of beta 1. And so there's a trivially, we have a surjection right here, right? So that surjects onto there. And the kernel of this turns out to be is the S torsion of R I, of the Rees algebra. So I have some torsion as a module over S. So this is a description of Rees algebra and symmetric algebra. And again, the reason we cared about this whole setup was that this thing, the Rees algebra was describing, this was the graph of our map phi, right? So that's why we care about this thing. All right.
So what you wrote down depends on your list of generators.
That's right, but it turns out not to depend on the choice of generators. Great question. Frank asked. So again, I'm being somewhat. I'm not going to say I'm being cavalier because I'm always cavalier. But what I'm trying to do is sort of give the flavor of everything without crossing every I and dotting every T. All right. So this is Rees and symmetric algebra. So now that was the turbo review, and now I'm going to write down the scary part of the talk. So here's two theorems, which we won't prove, but which we're going to sketch. So theorem 1. Let me make sure I get my, how did I want to write these out? Yeah. So I apologize. I don't like it when somebody's just sitting there writing and everybody's, you know, waiting for some shoe to drop or something. And let's see, and fit 0. All right, so let me parse this. So here's two theorems. The first theorem, this is some hypothesis. So what I'm going to suppress is the part of this that involves local cohomology, because for the hardcore algebraists, that would make them a happy face. And for the for the more applied folks, it would take a whole lecture to do the local cohomology. But these hypotheses are both hypotheses on certain local cohomology modules, which are not hard to define. but which would take too long. So these are hypotheses on local cohomology, so I'm going to erase them now. So the first theorem is that the kernel of our map phi is the annihilator as an S module of this Rees algebra, right? And remember what the Rees algebra was. I was taking a quotient of S tensor R, right? I was taking my polynomial ring in all the variables, both the x's and y's, and then quotienting by the relations. Here I'm going to think of this, because S is a subring, I can think of this as a module over S. I only take a certain graded piece of this, right? So I'm taking a certain graded piece and thinking of that and looking at the annihilator of S, okay? But this is hard. The point here is this is hard. And the reason it's hard, and I want to say it right now, is that this Rees algebra is hard. So I mentioned this before. So Rees algebras really, finding defining equations of Rees algebras is really, really tricky. So I give you an example over here. Here's, I guess, one of my favorite examples. So there's a paper maybe from a year or two ago of Andy Custon, Claudia Polini, and Bernd Ulrich, where they take what for commutative algebra is a very canonical example, Gorenstein codimension 3 rings. And this is sort of something where the resolution is known. It's a short resolution. It has 3 steps. It comes from Pfaffians. It's beautiful. It's nice. It's canonical. And to find the Rees algebra of this really simple canonical object takes them 30 pages. So even in really sort of standard cases, it's hard. And so finding Rees algebras is hard. So now what we do is we back off a little bit, as we usually do in math, and say, well, what if I'm in a nice case? So we call an ideal linear type if the Rees and symmetric algebras are equal. That's sort of the best of all possible worlds, right? If we're like, because the symmetric algebra is pretty straightforward. We understand the presentation. We don't have to keep taking powers of our ideal. We just look at the ideal itself. So in this case, when you're linear type, we have another nice theorem, which at first it also looks ugly because of these local cohomology hypotheses. This is what I was after, the kernel of my map phi. It's again the annihilator of something, which, because it's linear type, these look almost exactly the same, right? The Rees and symmetric, except I need a degree here. This degree depends on local cohomology. But why do I care about this? Well, somewhere in just a minute or two, we'll start talking about fitting ideals. And the point is, this annihilator contains the fitting ideal of this thing. This fitting ideal turns out, that's an ideal of a bunch of minors of some matrix. This is not bad. This is going to be a happy part. So you'll jump back in if you're zoning out on me in a second. And this fitting ideal, there's something called the Macrae invariant, which is just a polynomial. It's a single polynomial. This Macrae invariant that's like curly S. I can't do the Gothic thing, so you guys have to suffer. I guess it's not really suffering seeing somebody watch bad Gothic scripts. This is the smallest principal ideal that contains the fitting ideal. And so one of the simplifying assumptions I'm going to make is that we're just implicitizing a hypersurface. Assume. Most of what I'm saying works in general, but if you're interested in a hypersurface, then I want a principal ideal, implicit of hypersurface. All right, so these theorems look opaque if you're not already an expert, right? If you're not an expert, they look opaque, but what I want to do is step through the pieces here, because this thing, the point is that this is what we want. It's this annihilator, but this annihilator can be phrased in terms of fitting ideals. These are determinantal ideals, and these fitting ideals turn out to be related to things called the Macrae invariant, which is the determinant of a complex. So I got to do these things, but these are not so hard. I'm not going to prove theorems, so I want to discuss these now. All right, so you should wake up if you're asleep. I need to give there's an espresso prize coming up in the fitting ideals section. So you should wake up for fitting ideals. I should just stop giving prizes and save the espressos for myself. And it's kind of bad because I'm at 25 minutes and I'm only through part 2 of the talk. So I better maybe drink those espressos myself, right? So fitting ideals. So fitting ideals. So let's say S is a polynomial ring. This works more generally. S is a polynomial ring. It works for a domain. And M is an S module, finitely generated. Guys in back should be yelling at me. So, and if I have a finitely generated S module, just like groups, it has a presentation. So I'm going to take some presentation. S to the n goes to S to the m, goes to m, goes to 0. These are generators and relations. I'm not going to even worry about the gradings right now. I don't need that. So I have finite number of generators, finite number of relations, right? So this is my picture. So I have this. So then the definition lemma, maybe definition exercise is better, is that the fitting ideal, fit I of m, is by definition the ideal of m minus I by m minus I minors of A, right? In particular, fit 0, the zeroth fitting ideal, is the ideal of the m by n minors. And the exercise is that this is independent of presentation. Right? I might choose some other set of generators and relations, but when I take these ideals of minors, that's independent of the presentation. All right, so what, you say very reasonably. So, so here is a lemma. Fit 0. I'm going to suppress the, well, I'll write it in. M is contained in the annihilator of M. Annihilator of M is just the set of all elements of my ring that kill the module M. And if M can be gen by Q elements, then we get this containment. So what? So we're going to actually prove this lemma. So Rhoda says you should only prove tautologies. This is kind of a cute short proof, and you guys get a chance to win an espresso. But what's the point? The point here is that I've got the fitting ideal sandwiched between the annihilator of M and some power. This means in particular that the radical of fit 0 of M is equal to the radical of my annihilator. And it turns out that if M is torsion, then all the associated primes of M are minimal or contain the annihilator of M. So this is sort of an aside for the commutative algebraists. The point is that the annihilator of M captures really, really important information about your module. And this is going to come back in a second. But what's the proof of this? So proof. Wake up for espresso prize. So what I want to do first is I've got my presentation, s to the n goes to s to the m, goes to m, goes to 0. If n is less than m, and I'm working over a domain, so it turns out if n is less than m, it's trivial. The only thing that annihilates m is 0. So we want to assume that n is greater than or equal to m. I have more relations than generators. Otherwise, m is only killed by the 0 ideal. So what I do then is I pick something. This was my matrix A. I pick a submatrix of this, right? I want to think of this as sort of a long, skinny matrix because m is smaller than n. So I pick some submatrix. Let's call this A prime. And I have this picture. You guys are with me on this, right? So I've got some big matrix. I pick a smaller submatrix. And I'm going to call the kernel upstairs M prime. Right? So notice this M is M prime modulo a bunch more relations, right? So this is M prime modulo more relations. And this immediately means that, so there's a surjection right here, right? And in particular, the annihilator of M prime is contained in the annihilator of M, right? If I kill everybody here and this guy's a quotient, that means I kill everybody here. So the only thing I need to do, what was my mission? I wanted to show these maximal minors killed M. This is going to give me a maximal minor, right? So I need to show, with this, I just need to show that det of A prime times A equals 0 for A in M prime, for all A in M prime. All right. So I'm going to start the proof, and then we're going to have a pause for the espresso prize. All right. So what is M? M is, or M prime. This is just the co-kernel of this matrix. So A is in M prime means A is in the co-kernel of A prime. That means A is 0 if and only if A is equal to A times x for some x, right? The co-kernel mods out the image, right? Co-kernel kills the image, so A is 0 exactly when it's equal to somebody in the image of A prime. My bad. All right, for the espresso prize, second espresso prize, what theorem should I apply from our undergraduate linear algebra, only grad students from our undergraduate linear algebra class, what theorem should I apply to this problem? Or perhaps not a theorem, perhaps simply a rule. Yeah, I heard somebody mutter it. Some faculty member was unable. Was it a faculty member or not? Who said it? Who said Kramer's rule? All right, come on down, get your thing. So Kramer's rule, right? Get your espresso. Right? So the point is that A is equal to A prime x, but the point is that I can solve this. I'm trying to solve this equation, so by Kramer's rule, of course, we can solve this equation just by looking at A dot debts of these, debt of dot 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 A over debt A, and this is my desired x. And so multiplying on both sides, I get exactly that debt A prime A is going to be 0. And so this shows us that the determinant of that matrix annihilates everyone in the co-kernel. And so the determinant of this guy kills this, so that means in particular the determinant of A prime is in the annihilator of M prime, which is contained in the annihilator of M, and therefore the fitting ideal does annihilate everybody. So that was an easy proof. That's all we're doing on fitting ideals. So now we can check that one off. And now I'm going to go on to the Macrae invariant. So if you take nothing else out of this talk, you should take away the point that you can tell your linear algebra students, hey, there's nice applications to this, to fancy math that's actually useful in applications to geometric modeling, right? They won't buy that anyway. If they don't like linear algebra before, they're not going to like it now after you tell them that. So, all right, so that's that. Macrae invariant. And we're going to put all these pieces together at the end and see why that example that I started at the beginning worked out. So the Macrae invariant. All right, so this is section 3. Suppose that I have a finite free resolution. So these are free modules, maps between them, of some module M. These are free modules, just modules that have maps that are matrices of polynomials between them. And I want to suppose that each of these has rank n. So this has rank Rn, Rn minus 1. These are the ranks. And I want to assume one thing. I want to assume that the summation minus 1 to the I, R sub I is 0. The sum of the ranks is 0. That is equivalent, and I want to work over a domain. This is the ring is a domain. And this assumption says that M is a torsion module. This is that M has rank 0, and so it gets killed by things. So this is our setup. And then I'm going to define something called the Macrae invariant, which is a special case of the determinant of a complex. We know how to take determinants of matrices, but I have a whole complex here. I have all these matrices of polynomials. They're not square. What in the world could it mean to take the determinant of such a thing, right? I mean, that seems kind of senseless. So the way we do this is the following. Let's look at this first matrix. This has full rank. This has rank Rn. This is a free resolution. So this is an exact sequence, right? The image of one map is equal to the kernel of the next. So this is exact. EXACT. So what I do, because it's a domain, that means this map has full rank. So I can find some Rn by Rn submatrix that has non-zero determinants. So I'm going to make that my top. So this is going to be called alpha n, beta n. This is a Rn square matrix, and det of alpha n is non-zero. And the reason I can do that, again, it's a domain I can localize. This has full rank, and that's it. So this is easy. So I've made a choice, right? And now what I do, as soon as I do the next step, you'll see how we keep going. So at the next step, I look at this matrix right here, and I'm going to factor it into pieces. So the image of this map is the kernel of the next map. So I want to break this matrix into sort of two chunks, one of which is in the kernel of, dn minus 1. Let's call this dn minus 1. And the other which is going to tell me the image, right? Just like linear algebra, the rank plus the nullity is equal to the dimension of the source space, right? So this had rank Rn. The image of this is the kernel of the next. So I'm going to put my kernel up here. So I'm going to make some matrix here, Bn minus 1. This is Rn by Rn. And this is capturing kernel, right? So this guy is going to be in the kernel portion sort of this next matrix. And then what I have is the piece that's going to be the image. So this is going to be an Rn minus 1 by Rn minus 1 minus Rn by Rn minus 1 minus Rn bit. which is going to be my alpha n minus 1. And I don't care what's going over here and over here, right? So again, if you wanted to think about this purely in linear algebra terms, because I'm over a domain, I could localize. If I localize, I have a field. If you're over a field, you can obviously do this kind of factorization of matrices, right? So I've done this. And now I just keep going. I can make these same sorts of choices all the way down. So I keep on going. So the Macrae invariant, so what do I get? And I should say one last thing. At the last step, I have over here from F1 to F0, I have some matrix that looks like this. And I'm going to factor it as beta 1, alpha 1. And the point is, what's the rank here of this thing? Notice this matrix had rank n, Rn. This matrix had rank Rn minus 1 minus Rn. The next one is going to be Rn minus 2 minus this rank. And so the point is that this matrix at the very end, the rank here, is going to be R1 minus R2 plus R3 minus R4 dot dot dot. That's the rank of this map. But because of our hypothesis here that the sum of the Ri's equals 0, that means exactly that this guy is equal to R0. That means this last matrix has full rank, and so I'm just going to, this thing is going to be, this thing will have full rank at the last step, and that's from the hypothesis there. So what? So the Macrae invariant, so curly S of M, is by definition equal to, I could write this out more carefully with some alternating thing, but you guys will get the idea. Det of alpha 2, det alpha 3, det alpha 4, yada, yada, yada. Goes on, right? So I take the product of these determinants divided by a quotient, right? This seems like some random object. Who cares, right? You guys obviously are looking like you need the last espresso. So here's the theorem on these. And this is, again, not a hard theorem to prove. The theorem, if this is independent, S of M is independent of the choices. Who cares, okay? So there's other nice properties, which I won't write out. It behaves nicely under localization. It's multiplicative on short exact sequences. But the cool thing that we want is the following. S of M is integral, right? A priori, this is not going to be in your ring, right? This is a quotient of somebody in your ring by somebody else in your ring, right? There's no reason it should be integral, but it is. It's integral, and it's even better than that, and is the smallest principal ideal containing fit 0 of M. So we know the fitting ideal annihilates a module. If I know that I've got a hypersurface, remember what we were trying to do is try to understand the annihilator of something. That meant understanding a fitting ideal. If it's a hypersurface, I should have a single equation. That means that the Macrae invariant is going to play a role here because it's the smallest principal ideal that contains my fitting ideal, right? And so that's Mr. Macrae invariant. So this is going to be why Macrae invariants pop up. And so I should say, actually, a lot of this is appears very nicely and cleanly written out in a paper of Laurent Bouzet, Marc Chardin, and Joan Leloup. So that's the end of Macrae invariants. And now I want to do the determinant of a, that was the determinant of a complex, actually. Oh, that's good. I only did have 6. I thought I only had 6 sections, so we can actually cross off 2. So now we're on to approximation complexes.
Yeah, I was about to ask you if that was the determinant of a complex.
It is. So exactly right. So this is how you do the determinant of a complex. And again, it seems like some totally funky thing that there's no way that this would be well defined, right? But it is. So approximation complexes. There will be a chance for the final espresso prize coming up in the approximation complex section. All right, so approximation complexes. This, by the way, I should say something here. The discussion of the determinant of a complex in Macrae invariant, this is, so fitting ideals, a nice place to read in this, read about this is in Eisenbud's book, which is sort of a canonical text on commutative algebra. A nice place to read about Macrae invariants and determinants of a complex is either, there's a book of Northcott, C-O-T-T, called free resolutions or finite free resolutions. You can also read this in a fancier exposition in the book of Gelfand, Kapranov, and Zelevinsky, which is a harder text. I find this to be more approachable, but let me put GKZ. All right, approximation complexes. So this piece of the talk is work of Herzog, Simas, and Vasconcelos. So approximation complexes. So we're still in the setting of I had an ideal generated by F1 up through Fk, contained in R equals k of x1 up through xn. And then I had my S was k of y1 up through yk. So what's the approximation complex? So first I want to define something that David mentioned, but which might be foreign to some folks. So that's the Kazul complex. So the Kazul complex let's just do, I'm going to do a simple example with k equals 3. So F1, F2, F3. And the point is that as soon as I do it for this, you'll see what it is. So I could write it out using exterior powers, but why use fancy notation when something is really rather simple? So the idea here is that I have my polynomial ring R3. I'm not even going to write down the gradings. It goes to R, and this is my F1, F2, F3. Right? So I have this map. So now, there's some things that are in the kernel of this map that are completely obvious that don't depend on what those polynomials really are. And these are called Kazul syzygies. And the point is that even our, well, I won't, it's easy to see some things that are trivially in the kernel of this map, because if I take F2 times the first minus F1 times the second, it vanishes, right? So that's a Kazul syzygy. So what I get here is I have a matrix, which is F2 on the first minus F1 on the second and 0. Then I have F3 on the first, 0, and minus F1 on the third. And then I have 0, F3 minus F2. And I have 0 there. So these are called Kazul syzygies. They're sort of trivial syzygies. And then what's kind of surprising here is that the process continues, and it works out really nicely. So in fact, what I have here is I have F3 minus F2, F1. And I have an R, and the process stops. And you can see this guy's actually, if you test it, it's actually in the kernel, right? F3 minus F2, F3, F1, and minus F2, F1. So this guy is really in the kernel. And so this is the Kazul complex. And more generally, the point is that if we wrote this out in fancy language, what I would be doing here is if I had a Kazul complex on F1 through Fk, I would have R to the k goes to R. That's my ideal. And then I would have wedge 2 of Rk, wedge 3 of Rk, and so on. And you can see that this goes back wedge k of Rk, and the last map is exactly the map here. It'll be my Fk up through F1 with appropriately chosen signs. So the Kazul complex is self-dual in a sense. If you HOM this into R, you'd flip everything. So the Kazul complex is not a hard gadget. And so what an approximation complex is something that sort of takes as its building block Kazul complexes, but I'm going to have two Kazul complexes floating around. And what I'm going to have is I'm going to start out with a Kazul complex on my FIs. Okay? So let me erase this bit. Maybe I erase up here. And what I'm going to do is each of these maps has a kernel and an image. This is not, right? The point is, this is certainly in the kernel, but if these are honest-to-God polynomials, we already saw in our example with the four things that the minimal free resolution just looked like this, right? So this was with our, this was our four example things. So the Kazul complex is typically not exact, and in fact, it's exact. David mentioned something earlier. He used this phrase, a regular sequence. So a regular sequence means it's a sequence of polynomials, f1 through fk, such that, of course, f1 is a non-zero divisor on your ring, because your ring is a domain. But f2 is a non-zero divisor on R mod f1. So geometrically, what you want to think of a regular sequence as being is it's completely intuitive. I start out with one hypersurface, f1. You hand me another hypersurface, it chops my dimension down by one. It intersects the first hypersurface transversely, right? So now I'm in codimension 2. I chopped it. With three things, I should be codimension 3, right? I want to chop each time, just like hyperplanes, right? Each time I chop, I should lose a dimension, that's what it means to be a regular sequence, is that I lose a dimension each time. And so if you are a regular sequence, which geometrically is called a complete intersection, which makes sense, right? Each time you intersect, you get something that's one dimension lower, then this is exact. And it's an if and only if. The only time the Cazul complex is exact, if this is a regular sequence or geometrically a complete intersection. So what I'm going to do then, to build this, or what, I shouldn't say what I'm going to do, what Herzog, Simas, and Vasconcelos did, is they took the kernels of these maps. So this is my, let's say this is D2 Cazul, this is D3 Cazul, D1 Cazul, and so on. So they take the kernels. The kernel of this is going to be Z2, this is Z1, Z0, or Z3, whatever. These are going to include, right? These are the kernel of these maps, so I have inclusions here. These are modules over my ring R. I erased my ring, which was terrible, so R was K of x1 through xn, and my S was K of y1 up through yk. These are R modules. There's no S in the picture right now, right? You guys are with me? You guys in the back that aren't asleep? Yes? All right. So these are R modules. So I have these kernels. And now what I do is I tensor these with S. I'm allowed to do that. I can tensor with S. All right? I tensor with S. There's a Z0. Right? And now I'm going to put a new differential on the complex up here, which is kind of funky. The differential I'm going to put on the top is, I'm going to call it D3, I'm going to call it T, or S rather, D2S, D1S. And this is going to be, these are just Cazul differentials, but they're Cazul differentials using the YKs, right? So I'm using the YKs. So these are Cazul differentials using the variables of S, okay? And this is called the approximation complex. This is the approximation complex. All right, so two things. First off, one of the things you always check, in any homological algebra course is you've built something, is it really complex, right? I'm not even going to do that, but I am going to do one thing. I'm going to prove that this actually, at least that my maps end in the right place. I'm not going to prove that do the maps twice, you get 0, but let's check the maps end in the right place. So first is a little exercise that I give you guys. Let's call, instead of calling this D, I'm just going to call this, I'm going to write this guy as DF, and write this guy as DT, or DS rather. So the first exercise, which you should do if you're bored, is that DF DS plus DS DF is 0. This is not a hard exercise. You write things out symbolically and chase them, right? So what I claim is that then this little condition is going to show that if I take someone up here and I apply my dt, or my ds rather, to it, if I take a class here, I apply ds to it, that it ends up over here, not in some random space. So let's say that gamma is an element of z sub I. Z sub I tensor S, whatever. All right? So what happens when I hit, because this differential is 0, this means, of course, that df ds plus ds df applied to gamma is 0. The whole differential is 0, so this is 0. Now, gamma was already in a class in Cazul homology, right? So because gamma was a class in Cazul homology, this actually means that df already killed gamma, right? So this piece killed gamma already, yes? And that means, in particular, now we have that df ds of gamma is 0, but that says that ds of gamma, right, when I pushed it forward under that top differential, it's going to be in the kernel of df, which means it's exactly in z sub I minus 1, right? So it lands in the right place. Now, what you should do in the privacy of your own home is to check that, in fact, doing this differential twice is 0, and so on. All right. So that was the approximation complex. And the point is, why should we care about this? You know, this is some random homological algebra BS, right? Who cares? All right? Let's just take a check. So let's do a sanity check. Let's see what happens at the very first step, right? At the very first step here. And then notice the very first step, this Z0 is, the Z0 is all of R, right? Because I'm going to 0. So at the first step, sanity check. At the first step, I have Z1 tensor S goes to Z0 tensor S. This is just R tensor S, because Z0 is that. What was Z1? Z1 was the kernel of this very first map right here, right? My very first map was just F1 up through Fk, right? That's my first map down here. The kernel of this, notice, it's just the kernel. I'm not looking at Kazul homology right now. I just want the honest-to-God kernel of this map. And what's the kernel of this map? It's the syzygies on this, right? So this guy is, this is going to be sys of I, right? And so what do I get here when I compute the homology of this complex? This is my H0 of the approximation complex, is what? Help me out. Somebody for the last espresso prize. I'll open it to faculty. What do I get? I heard, who was the first that said symmetric? I think it was David. Congratulations, sir. Congratulations. So this is equal to S of I, right? So this is, but wait, but it's better. So the point is, what I get is the symmetric algebra, all right? So this is pretty cool, because what could happen, what if God smiled on us? So what if that was the only homology? If the when is this actually a resolution, right? What if this thing is exact the rest of the way? What if this is the only homology? Suppose H0 is the only non-trivial Hi of Z. That means that the approximation complex is giving me a resolution of S of I. And if you remember, it's long gone, but the theorem that we needed, to apply our theorem, we needed to get the annihilator of some graded piece of this thing, right? That's what I needed, was the annihilator of some graded piece of this thing. Well, if I have a resolution of this, that means that I can look in the graded pieces. When I look in the graded pieces, that's still exact, of course. And then all I'm doing is, and notice, this is the really important point. S is only a ring. S is only a ring in the y's, right? This is what we wanted, right? We wanted equations over here. And so the point is that just like when you look over a polynomial ring over a field, right? Your free resolution, when you look in graded pieces, those are just K vector spaces, right? It's exactly the same thing here. When you look at this free resolution, each graded piece is an S module. So this thing is an S module. If we're lucky, then we get a free resolution, we get the annihilator of this, and how do we do the annihilator? Oh, the annihilator was just some fitting ideal, which was some Macrae invariant, right? And so that's the whole payoff where everything works. So all that we need to happen is for a miracle to occur and that the approximation be a resolution, and also to understand what this degree is. Okay, so there's two things. So what Herzog, Simmons, and Vasconcelos prove, so at least for me, I always was wondering when I was first reading the literature, what's this LCI condition? Why do we care about base points being LCI? This is an if and only if the base points are an LCI. So there's your miracle. That's why locally complete intersection base points make everything happy, and we can run this machinery. So that's condition one. And the last thing I want to do is talk about this degree bit here. What's this degree thing? So here's two theorems, which again won't be proved, but which tell us what degrees we need, and which actually illustrate why base points are neat. So here we go. So if the base locus, so the degree that I need, nu, as soon as nu is greater than or equal to n minus 1 times d minus 1, this was the target projective space. These were the degrees of the polynomials. Then your degree is big enough for this theorem to pertain. Remember I said there were some nasty faces that said, with some local cohomology condition, that condition is what nu that we need down there. So this is if it's base point free. This is Bouzet, Chardin, Giannalu. This is if base point free. That is the base locus is empty. Then we take a nu in this degree. And if we have LCI base points, then we can take the same degree, and this is cool. I can actually drop the degree that I need if I have base points. Base points can be good. They can lower the degree of the equation. What is this? This is the degree of the smallest hypersurface through the base points. So I actually have 2 minutes left. And in the 2 minutes left, I want to return. I have another example, but instead of trying to work the whole example, I want to return to our start case, right?
So one thing I should mention is that the case I talked about, we're mapping to P3. That's when n is 3. So the n minus 1 becomes 2. So that's the 2.
Yeah, perfect. So as David points out, if I'm going from P2 to P3, this will be a 2, because 3 minus 1 is 2, times degree minus 1. So in our start example, I had those polynomials xyz, xyl, xzl, yzl. Let's talk about the geometry of the base locus of this. And L was x plus y plus c. So if we were so inclined, and we are, let's draw these lines. So here's x equals 0. Here's y equals 0. Z equals 0 is going to be the line at infinity. I draw it like this. And then I have the line x plus y plus c, which of course is going to intersect these guys transversely. So here's x plus y plus c equals 0. Right? The points, what are the base points of this thing? Well, you can see, as soon as two of my forms vanish, right? If x vanishes and either y or z or l vanishes, everybody's toast, right? X vanishes, kills these, y, z, or l kills that. So the base points are exactly these 6 intersection points, right? Those are my base points. That's the base. So they're visibly a local complete intersection, right? If I localize this ideal at, say, xy, everything outside xy becomes a unit. And what do I get? Well, everything outside xy is a unit means z and l are units, so I get an x. Z and L are units, I get a y, so I get x comma y when I localize, and that's exactly the equation locally of that point. So this is an LCI. The theorem says that we need to look in degree, as David said, we're going to P3. I need 2. My polynomials are degree 2, so 2 times 2. Looks like I need degree 4, but what's the smallest curve through all these points? Is there a quadrant through these points? Help me out. Could I have a quadrant going through these points? I gave away my espresso. I'm not giving away. I'll give away my partially eaten fudge bar.
All of the points?
Yes, I need a quadrant through all the points. Look at what's up there. Why not?
To contain one of the lines.
Exactly. If I had a quadric, I have to contain certainly these 3 points, right? But if I have a quadric that contains 3 points on the line, it has to contain the line. So any quadric would have to contain any line, but that means I'd have to contain all the lines, and visibly I don't. So I don't have quadrics, but I do have 6 points only imposed, 6 conditions. I got a 10-dimensional space of cubics, so there's plenty of cubics. So I take 2 times 2 minus 3 equals 1. I only need the degree 1 piece of the approximation complex. And that's why when we did the approximation complex, that weird matrix that I came up with, that was the only differential in my approximation complex. My mystery matrix, if you trace back through it, that mystery matrix is exactly the last differential in the approximation complex. That's why everything works there. And I guess in the last 2 seconds, maybe just for the classical algebraic geometers here, we know that if you blow up 6 points in P2, in our dreams or nightmares or wherever, I don't know. Having a Hartshorne student in the front row, I can say in our dreams, if we go back to section 5.4 of Hartshorne and read about the cubic surface in P3, we know that if you blow up 6 generic points, you get a smooth cubic, right? And we saw the cubic, we saw this cubic whatever, you know, minus y1, y2, y3, blah, 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 right? We had a cubic. It's not smooth though. It's not smooth. These are obviously not in general position. It's got 4 singular points. 4 singular points. And it's really pretty because the intersection theory, David mentioned intersection theory with a perhaps, I don't want to say jaundiced, but a non-committal. Let's use that phrase. David mentioned intersection theory with a non-committal perspective. The point is that the divisor that we're using here, these cubics, I'm using 3 times the class of a hyperplane minus my 6 points. This is the divisor being used to embed. I'm using the sections of this line bundle to embed P2 into P3. And if I want to know what's the degree of one of these curves, this curve is the class of a hyperplane minus the 3 points here, the blowup. So minus E1, minus E2, minus E3. And the intersection theory, the pairing on these blowups is trivial. I mean, it's just the pairing on h is h squared is 1, h times the ei's is 0, and the ei squareds are minus 1. So when I do this intersection pairing, I get this is 3. These minus ei's and these minus ei's, each of the squares cancel, so I get ei squared, so I get minus 1, minus 1, minus 1. That's equal to 0. Each of these lines in the image has degree 0. That means it's not a curve, it's a point. So each of these 4 lines, this line, this line, this line, and this line, gets contracted to a point. Those are the singular points on your surface. And so in terms of sort of the
cubics, you know, they either meet those 3 points, and they won't. A cubic to those 6 points will not really meet those 3 any other point on the line unless it contains one of the lines.
That's right, exactly. So those 4, that's the 4 singular points on your surface are coming from that, and that's the geometry of this example. So at any rate, we now sort of have maybe a not completely believable explanation of why that mystery matrix worked, but I hope you at least feel like you could go back and reconstruct the steps. So good place to end. Thanks for your attention. Questions? Nobody has questions because I gave away all my espressos, right? I can't emphasize strongly enough how pretty this confluence is between the abstract algebra and geometry and the honest applied problems. I think it's just a really cool area. And I still actually, my apologies to Lynn and to any other Rees algebra experts, because I'd never been excited by Rees algebras, and I can't believe how complicated they are. So anyhow. Yes, a question in back.
So can you make any statements about base points where it's not really a complete intersection?
There are some results on those cases. And my answer would be, read the write-up afterwards when David's book comes out. There'll be more stuff in here. And again, I mean, what I was trying to do was, instead of sort of giving the theorems far down the road, was to sort of fill in some of the blanks that you need to get to the proofs of the sort of core theorems, I would say. All right, well, thanks, guys. Have a great afternoon.